And welcome to the last lesson of our linear functions chapter. We're going to learn about linear programming today, also called linear optimization. So today we're going to be able to find optimized solutions by making a system of inequalities, and we're going to use linear programming to figure out how do I make the most profit? How do I wind up with the best outcome? This is what companies use all the time. People program computers to do this, where you put in parameters and you figure out how to get the biggest return on your product. So before we do that, I want us to reflect on this chapter. Okay, I want you to either make this table in your notebook, think about it for a minute, pause the video. Are you confident in each one of these skills, or are you unsure? And if you're unsure, what is your plan to get from unsure to confident? So pause the video, fill it out. Let's see where we are. Okay, so for today, we're really going to have to be confident, or at least working towards confidence in graphing systems of inequalities. If we can graph systems of inequalities, we can do linear programming. We're going to have to make the system, but we can do that. So what a system, or what linear programming is a method to achieve the best outcome, such as how to find the maximum profit, what should I make if I want the maximum profit, if I have different options. And we're going to have a bunch of linear inequalities. Now, optimization, to optimize means to make the best. Okay, there's generally one choice that's better than all the others. Sometimes there's two that are equal, but companies want to make stuff efficiently, effectively, and at the end of the day, they want to know that they've done the best job at getting the highest profit they can. So let's explore. Let's say I'm building cars and trucks. Okay, my cars that I'm building have 4 wheels. The trucks are a little bigger, they have 6 wheels. What are the possibilities of the cars and trucks I can build if I have 36 total wheels? So I want you to list as many possible cases as you can. Okay, for example, I can do 0 cars and 0 trucks, not use any wheels. I could do that. Okay, if I run a company, I could decide to do that. Probably go out of business, but I could do that. I want you to list at least 5 different possibilities. Maybe look at some of the other extremes. What's the most amount of cars I can build? What's the most amount of trucks I can build? What are some numbers in the middle? So pause the video, write down a bunch of ideas, and then I'm going to show you a table which organizes all. Okay, so you should have a few of them written down. Here's my table. So I can build 0 cars and 0 trucks, like I said. I can also build 0 cars and 6 trucks, because 6 trucks times 6 wheels is 36 total wheels. I used all the wheels. There's many options in between where I can use 8 wheels because I can make 2 cars, and then 4 trucks would be 24 wheels, and I would use almost all of the wheels. Okay, this problem doesn't say I have to use all of the wheels, and sometimes certain configurations where I have some leftover material is okay. Now, as I get to the bottom, I can make at most 9 cars. 9 times 4 is 36. That would use all my wheels. I got no trucks. And then 8 cars would use 32 wheels, and I don't have enough wheels left over to make any trucks either. Okay, so 9 cars, 0 trucks would probably be more optimal than 8 cars, 0 trucks. But we're going to learn that it really depends on how much profit do I get for each vehicle. If I'm making a lot more money on trucks, maybe I want to make more trucks. If they're about the same, we're going to set up equations and inequalities to help us find the optimal solution. Now, here's what it looks like. All of these different points represent possible solutions to how many cars and trucks. Now, my x-axis is cars and my y-axis is trucks. Now, I can see these top points are probably the ones that are most optimal, because why would I make 6 cars and 0 trucks when I can make 6 cars and 2 trucks? But I really don't want to test every single point. to figure out which one gets me the most profit. So what we're going to do is called linear programming. We're going to come up with graphing some linear inequalities, and we're only going to test 3, 4, maybe 5 points. And we're not going to ever make a bunch of points on a graph like this ever again, because this is not efficient. So we're going to look at a giant problem. It's going to take multiple steps. Feel free to pause the video anytime you need to write down more information. Okay, so our friend Abby, she wants to open up a company that builds cars and trucks. To make each car, she needs 4 wheels, 2 seats, and a gas tank. So it may help you to write down, okay, car, we need not 2 wheels, we need 4 wheels. 4 wheels, 2 seats, and 1 gas tank. And you may want to make lists of information so that we can write it into our inequalities. Okay, so we have a list for cars, trucks, and storage room. So what total materials do we have? Now we'll get to the last part later. What's the maximum profit she can make if she can sell each car for $2,000 profit and each truck for $4,000 profit? But the first step we're going to see is we got to write some linear inequalities to represent the parameters. So what are our restrictions? I can't just make 100 cars and 300 trucks. Okay, I'd run out of all the materials. So the first thing is, what is restricting us from making everything? So my parameters are also called restrictions, are my wheels, my seats, and my gas tanks in this case. In other situations, time is a parameter, hours or work hours, employees, anything that said once you go over it, you've run out of materials, that's a parameter, that's a restriction. So what we see here is we're going to have to write an inequality for everything that stops us from doing more. So 1 for wheels, 1 for seats, and 1 for gas tanks. Now, the wheels inequality, which we kind of used in our exploration, is we used 4 wheels per car, plus we used 6 wheels per truck. And we want that to be less than or equal to 36, because if it's more than 36, I got to go find more wheels that I don't have. Okay, I can't fit in my storeroom. So if you'd like, pause the video right now, write the inequalities you think exist for the seats and the gas tanks. Okay, so hopefully you did that. If not, here are the inequalities and we'll discuss them. There's 2 seats per car, plus there's 1 seat per truck, and we only have 14 seats total, so we need to use less than or equal to 14 seats. Gas tanks, same thing, 1 per car, 3 per truck, and we only have 15 at most. And then there's 2 other parameters that I like to write. You don't have to write them, but to me they just make sense. Okay, we obviously need to make a positive amount of cars. We can make greater than or equal to 0 cars and greater than or equal to 0 trucks. You can't make -6 cars. Once in a while, if you put ridiculous numbers in, it actually makes the profit go higher and it breaks our inequalities and breaks our equations. So I like to write down, do we need them to be positive? That also tells me that my graph only needs to be a first quadrant, so the top right part of the graph, and I don't need to make the giant T graph. Now that brings us to our second step, which is graph the inequalities. We have 3 inequalities. We know how to graph. We might not have graphed 3 at a time yet, but we can do that. And we're going to do it. So we're going to take our inequalities. They're all in standard form. I strongly recommend finding the intercepts, graphing the intercepts. So I put in a 0 and find 0, 6, because 6 times 6 is 36. I put a 0 in for y, and I put 4 times 9 is 36. And I do that for all of them. So once again, pause the video if you want to find the intercepts. If you want to graph it, okay, in a few seconds, when you unpause, I will just show you the intercepts and the graph. Okay, so here is our graph. Okay, well, there's our intercepts first. Should always write those down. This will tell me how big my graph should be. I need to go up to 15 on the x-axis and 14 on the y-axis. Okay, I'd probably go up by ones, maybe twos, but we got to graph accurately, so I see odd numbers, so I'll probably go up by ones. And I went up by ones, and I graphed the intercepts, and made my inequalities. Since it's equal to, these are always solid lines. Okay, and that's my system right now. Now I don't need to worry about over here in the negatives or down here, okay, because it can't exist. So really, my solution is down here, okay, right here. I'll write the word here. Here's where I got to look. Now I could test every single point here, and notice a lot of them are what we found in the exploration. I can make 6 cars, 0 trucks, 6 cars, 1 truck, 6 cars, 2 trucks, 5 cars, 1 truck. Now, if you want to test every single one of those points in the profit equation, go for it. But I'm going to show you we don't have to. There are much fewer points that we have to test. So, linear programming has taught us that we only have to test the vertices, the extremes. Okay, so on my graph, I only need to test the extremes. So I have a shape here that has this corner, this corner, this corner, this corner, and this corner, because I got to have greater than or equal to 0. So this corner generally 0, 0. Probably if I make 0 cars and 0 trucks, I'm not going to make a lot of profit. Once in a while, that point will make sense, but 0, 0 probably not something I need to test. Okay, I write down the coordinates because these are what I'm going to test into my inequality. Now this point is outside. It's still an intersection, but it's outside my shape, so I don't want to test it. Okay, don't write down, well, that's decimal too. We don't test that point. So I got 4. Maybe if you want to write 0, 0 as a 5th intersection point, and we're going to test them. So now we have a graph, we have our inequalities, we have the points that might make us the most profit. Now we need a profit equation. So we got to create an optimization equation from this situation. Okay, she's going to get $2,000 profit per car, $4,000 per truck, and I want to just find total profit. So in this case, profit is 2,000 times car, the amount of cars, plus 4,000 times the amount of trucks. So here's my profit equation. And I'm going to test every single point that I just found in the previous slides into my profit equation. So I'm going to test 0, 5, 3, 4, 6, 2, 7, 0, and 0, 0. And I like to do this all on graph paper. I have the graph next to the inequalities, next to the equations. And what I can do is test each point in. So I put 0, 5 in. Then I get $20,000, which is a good profit. Now pause the video, try the rest of them. Tell me which one gets you the most profit. Okay, so you've tested all of them, and hopefully you see that 3, 4, 6, 2, 7, 0, 0, 0. I just tested 0, 0, show you it gets no profit. And the winner is 3 cars, 4 trucks, and you get $22,000. So if you do linear programming, if you choose that option, you then get an extra $2,000 over some of the options. Or get a lot more money if you just only make 7 cars and 0 trucks, you only get 14,000. So this is what companies do. Now, there's a lot of people that write programs to help with this, but this is the math behind it. This is how companies are successful, knowing what's the optimal thing to do. So now, here's a few for you to try. Here's one. You can go ahead and pause the video, try it out. I will show the answer after a few seconds when you unpause. Okay, so this problem should have taken you 5, 10, maybe even 15 minutes, especially because you haven't done a lot of these in the past. Okay, What I see here is we want to maximize the points we get on the test. Our restrictions are how much time we have, and we can't answer more than 12 problems. So that's where my parameters are. I graph them. My profit equation, or my points equation in this case, I want to maximize my points. I get 6 points per computation problem and 10 points per word problem. And I find out that if I do 4 computation problems and 8 word problems, I get 104 points. Okay, I do exactly 12 problems. I maximize the amount of problems I did. I maximize the amount of points. I do really well on the test, and I'm super happy. So ultimately, we always want to know what the maximum score and what should I do to obtain the maximum, whether it's a score or a profit or a situation. Now I got one last example for you to try if you'd like. Okay, for those of you who like Harry Potter, so do I. So go ahead, read this problem, pause the video, try it out, graph it, write the profit equation, and find me a solution. Pause the video now. I will unpause it in a few seconds. Okay, so this one. Okay, this one we actually only have horizontal and vertical lines, which could happen. Okay, we have to make more than greater than or equal to 10 potions, but less than or equal to 25 potions. Here, same thing. More than 15 or equal to 15, less than or equal to 40. I test all 4 of these points. In this case, logically it says, well, if there's no restrictions, I probably should make the most potions at the most years. And that does happen in certain cases. Certain cases, it's very evident and apparent, and we don't have to make the graph. But most times I would just practice graphing the inequalities, see which one's the optimal solution on the graph, which one looks like it. We test it into our profit equation, and we find a solution. Okay? And that's what linear programming is. It's very challenging, but it helps companies increase their profits and figure out what the best thing to do is. So there will be more practice on linear programming. I don't expect us to be perfect at it yet, but it contains writing inequalities, writing equations, graphing inequalities, and a whole lot of skills that encompass this entire chapter.